This is going to be a video on Chapter 10.2, which deals with the areas of rhombuses, trapezoids, and kites. So let's go ahead and get this on here. So remember, the area of a rectangle, squares, and parallelograms is attained by, again, it's one of the more commonly known formulas. We either call it base times height, that's for the general, or sometimes we call it length times width if you're dealing with a rectangle, or some combination of these. So remember, a rectangle actually has a length and a width, as does a square, so length and width. But a parallelogram doesn't really have a length and a width in the traditional sense, but it does have a base and a height. So the bottom part here, this line here, is my base, and this line here would be my height. So we usually use this version of it, but sometimes it's been called this if you're dealing with a rectangle or a square. And a triangle is just half that. So a triangle is base times height divided by 2. Because if you think about a rectangle, and if I cut in half, I get a triangle. And I can do that for any triangle. So if I have, or put another way, I can take any triangle and build it into either a rectangle, a square, or a parallelogram. Even weird triangles like an acute triangle, I can, with a little bit of manipulation, make it into a parallelogram just by doubling the area. So the area of a triangle is half the area of whatever parallelogram it would have doubled into. So we're going to be looking at these new formulas using those as a reference. So for a trapezoid, remember, it's a little bit different. It's a little bit more difficult to visualize, but think about taking a trapezoid, and then you are taking, let's see, this green line here, this is the top base here is the green line. You're taking a trapezoid, you're doubling it, and then you're turning it on its side. And if you put them together, you get this new parallelogram here. Let's see if I can't get out of this here for a second. There we go. So let me go into this here. So think about taking this trapezoid. If I refold it here, you're taking this original trapezoid, you're doubling it, and then you're turning it on its side and putting it together, and lo and behold, now you have a parallelogram. Well, your goal then is to figure out, okay, how do I get the area of this original trapezoid? Well, the area of this original trapezoid is going to be half the area of this entire parallelogram, right? Because this new parallelogram I made is basically two of these things put together. So if I can get half of this entire shape, I can get my answer. Well, how do we do that? Well, let's go ahead and go back to my little thing here. So how do we do that? Well, the area of this trapezoid, or the area of this parallelogram, rather, the entire parallelogram we know is base times height. That's the area of this entire parallelogram. I want simply half that. So I want half the base and height of this parallelogram, which almost sounds like a triangle. That's because a trapezoid is kind of halfway between a triangle and a quadrilateral, although it is a quadrilateral, just kind of in terms of concept. But how can I modify this a little bit? Well, what's the base of this trapezoid? Well, the base of this trapezoid is basically the base of the bottom base of the trapezoid. I'm sorry, let me rephrase that. The base of this parallelogram, I said trapezoid there. The base of this parallelogram is the bottom base of the trapezoid plus the top base of the trapezoid. So if we call this one B1 and we call this B2, that means the base of this trapezoid is simply the top base plus the bottom base, right? Those make the base of this parallelogram. And the height of the parallelogram is the same as the height of the trapezoid, right? This height right here is the same as this height right here. So the height doesn't change, h doesn't change. And I'm still dividing by 2. So this is where we come up with the trapezoid formula. The trapezoid formula is the top base plus the bottom base times the height, then divided by 2. Because again, the top part of this fraction gets me the area of the entire parallelogram that would be made if I doubled it, and then I cut in half because I only want half of it because I just want the trapezoid, not the entire thing. So this is the area for a trapezoid as it's typically written. Sometimes it's written as 1/2 times base, or times base 1 plus base 2 times height, but I usually write it as a big division by 2 just because that's how I think about it. So, but that's how this comes about, is you take a trapezoid, you double it, you make it into a parallelogram, and then you half that total area. That's where this area formula is derived from. So let's try this a little bit. So here we have a trapezoid. Everything's nice and labeled, so no big deal there. We simply take base 1 and base 2 and add them together, so 6 plus 8. Then we're going to times that by my height, which is 4, and then we're going to divide it by 2. So 6 plus 8 is going to give me, let's see here, that would be 14. And then 14 times 4 is going to give me, that would be 56. And 56 divided by 2, that would be what? Be 20, I'm doing this in my head here, just give me a second, 28. And so that would be 28 units squared for this area, assuming I did my math right, which I believe I did. So again, no big deal, just plug and chug. That's all there is to it. For a right trapezoid, which is what this is, it's a little bit more difficult to see, maybe, but the height is this line right here. The height is the 4, because that's the line that connects the two bases. So if you're ever wondering what line of a trapezoid is your height, it's the line that connects the two bases. So if 5 is my base 1 and 8 is my base 2, which they are, so 5 plus 8, because they're the parallel sides, then that means that 4 has to be my height, because that's the line that connects them, and then divide by 2. So that'd be 13, and then 13 times 4 divided by 2 would end up giving me 26 meters squared, if I'm being appropriate by labeling it. And then this one down here is the same deal, it's just on its side, right? So it's still going to be 7 plus 15, and then we're going to take that big thing and multiply it by 15, and then divide that by 2. So 7 plus 15 is going to give us 22, and then 22 times 15 divided by 2 is going to be some rather large number, so let's go ahead and calculate that out. 22 times 15 is 330, divided by 2 would give you 165. So 165 meters squared. Right? So again, no big deal for a trapezoid. It's one of the more complex formulas, but once you know how it's derived from, hopefully it'll be a bit easier to memorize. And again, it's only 3 pieces: base 1, base 2, and height. So don't use the diagonal slanted pieces when you don't need to. For a kite and a rhombus, it's a little bit different. Because they're not as nice, but you can think about them as basically a bunch of right triangles, right? So if I have a rhombus here and I draw its if I draw its diagonals, they're going to be perpendicular to each other. So I end up with 4 right triangles, and same for a kite, although the right triangles in a kite aren't all congruent, but I still end up with 4 right triangles, 2 congruent triangles on top and 2 congruent triangles on bottom. So we get the area of this, and I'll spare you the derivation, but it's possible. The area of this is 1/2 times the first diagonal times the second diagonal. For both of these, both rhombus and kite have the same formula. So we can call this one diagonal 1, and we can call this one diagonal 2 if you like. It really doesn't matter which one's 1 or 2, as long as you have one be 1 and have one be 2, you're good. Right? So that's the area. Again, we can go through the derivation maybe another time, but it has to deal with the fact that you have a bunch of right triangles in here, and you combine their areas, and it ends up canceling out to that essentially. So once again, pretty common practice here to do, like for this first one here. Now, I'm not really clear that these means the entire side, but it does. So 4 is the entire length, 7 is the entire length, so the area is just 1/2 times 4 times 7, which ends up being 14 centimeters squared, again, if we label it correctly. For this one here, they actually labeled the diagonal into individual pieces, so be on the lookout for that. So in this kite here, I'm going to multiply 8, which is the entire length, times will be 8.5, which is the entire length here, and then times 2, or then times 1/2. Right? I wrote my 1/2 on the back end rather than the front end, but it's still the same deal. So 8 times 8.5 times 1/2 would be how we tackle that one, because again, we have to add up the pieces to get the full lengths of the diagonals before we go and work with them. So this would be 34 feet squared. And then for this one down here, once again, we have that AC, the entire length is 8, BD, the entire length is 6, so no need to add stuff up here. We can simply go straight to the formula. 1/2 times 8 times 6. Because once again, they tell me what the entire lengths are, so I don't need to do any funny manipulation like I did in the last one. So that's mainly the big trick here, is that sometimes they give you the diagonals in pieces rather than as wholes. So this would be 24 meters squared. And then lastly, this one here, again, it doesn't really explicitly say, but it looks like this 10 represents just this length, and the 14 represents just this length. But remember, in a what looks to be a rhombus here, the diagonals are going to bisect each other. So that means that this side over here is also 14, and this side over here is also 10. So it'd be 1/2 times 20, which is the full length of the first diagonal, times 14, or sorry, times 28 rather, which is the full length of the second diagonal, which would end up giving you 280. But again, assuming this was a rhombus, which it didn't say, but we can assume that is a rhombus because I made it. So rhombus, the diagonals are going to bisect each other, so sometimes it might only give you half, and it's up to you to fill in the other two pieces, knowing that property there. For a kite, it doesn't really work that way because the only one that gets cut in half is the short diagonal. The long diagonal isn't cut in half, so they have to give you those. And then lastly, again, we're just going to get to the last one there, but knowing the properties of the diagonals, especially for rhombuses and kites, are necessary, and making sure you know the Pythagorean theorem is also necessary because sometimes you have to fill in the missing pieces before you tackle the area. So for example, here's a trapezoid. I want to find the area. Well, I need the height in order to find the area, and I don't know that yet. I know that base 1 is 10. I know that base 2, which is this entire length here, is whatever 27 plus 15 is, right? Because I want the entire length. I just don't want 27 and 15. I want the entire length there. So 27 and 15 are going to give me 42. And then I need to know what this missing piece is here. Well, I have a right triangle, so now would be the time to use Pythagorean theorem. With this is my hypotenuse. So it'd be a squared, we'll call this little a, plus 15 squared equals 25 squared. So once again, the Pythagorean theorem is a necessary piece of information, and we've done that stuff before. If you don't remember, you can go back to past videos and look at Pythagorean theorem, but you have to kind of do a little bit of right triangle work here before you actually end up getting the area. So to spare you the calculation, this ends up being 20 for A. All right, so again, we just go through the Pythagorean theorem, and then we do the formula for the trapezoid. So base 1 plus base 2 times the height all over 2. So 10 plus 14 is 52, times 20 divided by 2 would end up giving you 520. So again, a little bit of Pythagorean theorem needed there to find a missing piece before you dive into the area. And then same thing for a kite, right? Remember, for a kite and a rhombus, the diagonals are perpendicular. So that means that this is a right triangle, which means that I can use Pythagorean theorem to figure out how big that side is right there. Which, this is actually a triple. It's the 5, 12, 13 triple. So this is actually going to be 12. And because it's a kite, I also know that this side here is going to be 12 as well, because in a kite, the short diagonal is bisected. And also, I then need to figure out how big this bottom piece is here, right? Because I don't know how big this piece is right here. This is not bisected by 5. So then I have to use the right triangle or Pythagorean theorem again to find out how big this bottom piece is. So that's when I don't really recognize this triple, at least not off the top of my head. So I have to actually do the Pythagorean theorem here. So it'll be 12 squared plus y squared equals 17 squared, because 17 is my hypotenuse for that bottom triangle, because remember there's a right angle right there. And then you go through the theorem again there. So once again, make sure you're careful with what you believe is bisected and what's not, because in a kite, only the shorter diagonal is bisected, unlike in a rhombus where they're all bisected. So again, a little bit of a issue there. So let's see, 12 squared is 144, 17 squared is 289. So I'm just kind of doing this off the cuff here, so give me 1 second here. I'll spare you again the calculation. Should end up being y is roughly 12.041 is what I got. Hopefully my calculations are correct there, although I'm sure somebody will let me know if they're not. And so then I can do my kite formula. 1/2 times whatever 15 plus 12.041 is, would it be 17.041? Again, this is gotten from taking 5 plus this, adding these together to get my full diagonal, and then plus 24, because once again, I'm adding these together to get my full diagonal, right? So 1/2 times 17.041, or yeah, times 24, and I get 204.49. 204.49. So again, just because you know the formula doesn't mean you know how to do the problems. You need to make sure you recognize and use past experience, both on the property end, so knowing what the properties are to kind of figure out what situation you're in, and then stuff like Pythagorean theorem and old school stuff that lets you fill in those missing pieces, missing gaps when you need to. So that's it for this video. Hopefully helped you out. Once again, make sure that you know how to incorporate other stuff than just the formulas and the problems, because you're going to need more tools in your toolbox than that. Again, hopefully this video helped you out, and have a good day.